Hi, I'm Brad Knox, and I'm going to talk about a framework called Tamer that learns control from explicit human feedback, and specifically an implementation of Tamer on a robot. This work was all done jointly with Peter Stone, and the robotic portion, Cynthia Breazeal, was also a collaborator. First, I'm going to talk about the Tamer system, just introduce it briefly and give an overview, and then I'm going to talk about that implementation on the robot Nexi. But first, let me talk about the overarching research goal. We want to empower users who may not have technical training to customize and teach new behavior. The number of applications is vast for this broad problem, and it includes things like having assistive robots, training video game characters, and also working on an assembly line with robots and needing to customize their behavior. There are a number of different ways that robots can learn from human teachers. I'm only going to talk about the first one here, learning from scalar feedback, but there's also learning from demonstration, often called imitation learning, and going by specific forms of behavior cloning or inverse reinforcement learning, learning from advice, and so on. There's some others as well. First, let me give a somewhat of a hand-wavy definition of human feedback. The hand-waviness, I think, is somewhat necessary because we are talking about something with a human element. And so the hand-wavy part is about what the humans are actually, what their mental model is and what it means when they give this feedback. But what we mean, communications of approval, disapproval, reward, punishment, something in that kind of sphere of ideas of positive and negative feedback signals that can be intuitively mapped to a numeric signal for the evaluation of agent behavior. So I don't mean advice and I don't mean demonstration. I just want to be clear about that. I'll also briefly note, I used to call this human reward. That specific terminology didn't catch on, and I might accidentally refer to it as that. At least one diagram has it written as that. To give a sense of what this learning from explicit human feedback or from human feedback looks like, here's a Tetris agent acting randomly. It's just randomly choosing piece placements. And here's a training session where after a placement, the black box at the top left will flash red when a -1 feedback is given and green for a +1. And feedback can be given from the time of the placement to the time of the next piece's placement. And if a button is pushed, so if a button is pushed multiple times, that's a stronger amount of feedback. So the label for a placement, if I push the positive button twice, 2 green flashes would be +2. If I push the negative button once for a placement, then the label would be -1. So that's what the interface looks like, and you should be able to tell it's already doing better than random. Not fantastic, but better than random. And here's after 2 games of training by an expert trainer. In our actual experiments, we don't have expert trainers, and they are also more often than not able to train behavior that at least qualitatively meets the threshold for looking like successful training. And one thing I won't get into here in detail is that teaching with Tamer, much like teaching from demonstration, can often get to good behavior much more quickly than standard reinforcement learning algorithms. So the first part of the talk here is going to be introducing our system for learning from this type of human feedback, which is Tamer. You can see on the left here the typical diagram for reinforcement learning agent environment interaction. The agent takes actions, that changes the environment state, and then that's new states communicated to the agent along with a reward that provides feedback on that action and state. On the right is the Tamer diagram, and you still have the agent on the bottom, environment top right. There's now a human who can see what's happening in the environment. The agent is acting in it. And then the human's giving delayed reward, really feedback. There's the reward sneaking in, delayed human feedback. And there's 3 main modules that the Tamer agent has as it's acting in the environment and receiving this human feedback. The first is the credit assigner module. So the credit assigner module exists because of a recognition that people can't react instantaneously. So there's going to be some delay in their feedback. And so the credit assigner roughly takes a feedback signal and spreads it around on recent state action pairs. The end result of this is a sample for every state action pair, where the input, this is a supervised learning example, the input is a state and an action, and the output is a human feedback after modification from the credit assignment. The supervised learner can be really any regression algorithm, and it's going to output this reward model that the action selector uses to select actions. And what that action selector does is it says, okay, here's my state, and for every possible action, I'm going to query the reward model that's been learned so far, and whichever action is predicted to get the highest human feedback value, that's the action I'll take. So the action selector is greedy with respect to predictions of human feedback. And I'll also just mention that the need for algorithmically driven exploration is much lower with Tamer because the human trainer can give negative feedback to actions they don't want to see, thus driving exploration because the agent then chooses new actions. It's worth noting that maybe the most salient and important feature of the Tamer framework is that it turns what seems to be a reinforcement learning problem into a supervised learning problem. And I think that's part of what allows it to learn more quickly in many cases than reinforcement learning algorithms using regular environmental reward. Tamer has been implemented successfully on a number of simulated tasks, some by us, some by other groups. And I won't talk about any of these in any further depth. Actually, I'll mention Atari bowling was an extension to deep learning. And that's definitely an interesting paper to look at. And none of those tasks are robotic. And so one of the big questions is, will Tamer work on robots? So I had an opportunity in the summer of 2011 to be in the MIT Media Lab and implement Tamer on the robot Nexi. So here's the task environment. It's very simple. All that really matters here is the training artifact in Nexi. The training artifact is what I'm holding to my chest. It's picked up by the Vicon infrared camera system that's circling around us, the red glowing things. And what we draw from it is these two bird's eye view state features. The state features here, there's two of them. It's just the distance and the angle to the training artifact. Nexi here has its arms out, kind of like a zombie, just to make it clear which direction's forward. And in the actual experiments, Nexi's arms were just hanging down. And the actions, there's 4 of them: turn left, turn right, move forward, and stay put. And the reward interface was a presenter's remote where the right and left button were positive and negative feedback signals, respectively. There was a button for toggling training on and off. That's an important feature of Tamer that I think a lot of people end up missing, is that if the trainer's done training, it's a very small implementation, a line or two, to be able to just turn learning off and have it act according to what it's learned so far. And then also there is a safety button, because sometimes Nexi would start to run into furniture and so on, and that would just force the stay action. The core things for Tamer's implementation here are that we did regression to create the model of human feedback by key nearest neighbors, and the time step durations and the target velocities are shown here as well. And I'll talk a little bit later about these time step durations. We taught 5 different behaviors, and this is really the second goal of the research. So the first goal was to show Tamer can work on a robot. The second goal was to show that it can flexibly train different behaviors without changing the code, only changing what the trainer's doing. And before I get into those 5 behaviors, I want to talk about the novel aspects of this being a robotic training task. So we had some early failures in training sessions that were based on lack of transparency about what the current state action pair is. So you kind of think of this as trainer-agent mismatch about what the current state action pair is. And this took 2 different forms, the start and the end of actions. What happens here is, Nexi's acceleration is not particularly high. So if Nexi goes from staying to moving forward, say, there might be, just to throw a number out there, a half second where Nexi has not accelerated enough to actually know that the current action is to move forward. So Nexi looks like it's in a stay action, even though it's moving forward. And so the solution ended up being just to lengthen the time steps. I think something more elegant could probably be done. But basically by lengthening the time steps, then like say for moving forward, the time step was 1.5 seconds. Maybe the first quarter or half second, it was technically moving forward, but not visually moving forward. But then the rest of the time step it was. So that means a large portion of the time step, the agent's action is also the action that the trainer thinks is the action. The second one is the state of the training artifact. This Vicon system would sometimes lose it. And early on, this created some very confusing results of learning. And the solution ended up, after really digging into it and figuring out what the actual issue was to add an audible alarm. So whenever the Vicon system couldn't detect the artifact, and therefore the robot couldn't detect it, there was an alarm. And that allowed me as a trainer to quickly move the training artifact so that it would be detected and possibly turn training off for just a moment. I think it's really worthwhile to mention here that these problems are very similar to what are called correspondence problems in imitation learning or learning from demonstration. And those are where the demonstrator's state space or observation space and their action space can be quite different than the agent that's going to be learning from their demonstrations and performing the task. There's a lot of thinking about that problem that's interesting to read on. But I think it's interesting that it's very similar, but it's a little bit different. That for learning from human feedback, the issue is about the trainer's mental model of what the current state action pair is. All right, so here's the first of the 5 behaviors. Keep conversational distance. The robot's task, the correct behavior, was to turn towards the artifact and then move towards it until the artifact is at a reasonable distance to have a conversation with. So kind of pretending it's a conversational partner that you're approaching. So I'll first talk about turning left. So this is a representation of the model from bird's eye view. In each case, we've got Nexi again with the arms forward. And so this is if, based on the state, where the training artifact could be to the left, to the right, behind, or in front of Nexi, what's the prediction of human feedback if the actions turn left? So this is the same thing if the actions turn right, and so on. So for turn left, what we want Nexi to do is if the artifact is over here, it should turn left. If the artifact is over here, turn left's not a very good choice because that's turning away from the artifact. And so we actually do. So we actually do see that the predicted feedback reflects that. We see green, which is bright green, is highly positive. Black is near 0. And red is is negative, bright red, highly negative. And we see that when the artifact is to the left, that Nexi expects to get positive feedback, highly positive feedback for turning left. So that's good. We see the mirror image roughly for turning right, which we would want. And then for move forward, we see this bright green area for when the artifact is in front of Nexi, but not very close. And the bright green for stay is when the artifact is in front and close. So that really fits kind of if you were just going to code up the behavior as I described it while talking about it up here. It really fits that pretty well, but with some noise and kind of jaggedness to the model. One thing that I think is worth mentioning is that, so move forward here does have a prediction of positive feedback if the artifact is far to the left over here and Nexi moves forward, but it's not as bright green as turn left. So it's not actually going to move forward if the artifact is over here. It's going to turn left instead. And actually the jaggedness is going to be denser where there's more feedback. So you can see that it's not that dense. So there actually wasn't a lot of feedback here, which means that probably it mostly did turn left when it was supposed to be turning left in that area. Okay, so here's a video of training, and what happened is randomly Nexi chose to stay first, and you can see the white box there indicates that. And so what I do as the trainer is, I think in the paper we call it reward painting. I take the artifact and I move it to where stay is appropriate. So you can see I'm kind of at a conversational distance here, and I'm giving a lot of positive feedback here. Then I'm going to move to where it's not appropriate in just a moment. So watch I've given a lot of positive for where it should stay, where Nexi should stay, and then I move away where Nexi should not stay and give a negative. And that makes Nexi try a new action. And so I repeat the process doing reward painting by moving the artifact to all the areas, just a representative sample of the areas where Nexi should turn left. So see, I'm to the left, and Nexi should turn left towards the artifact, giving a lot of positive feedback. And then once I feel that I've given a lot, in a variety of situations where Nexi should turn left, then I move to where Nexi should not turn left and give a negative piece of feedback, making Nexi choose a new action. And so this is kind of the process to train each action, and then the rest of it is kind of testing for little, the remaining errors and giving more feedback on those to sharpen what it's doing. And at the end, you can see the model looks like what we just looked at in the last slide. Here are the 4 other behaviors. So we have go to, which is almost the same as keep conversational distance, but Nexi goes all the way to the marker instead of stopping the artifact, instead of stopping at a conversational distance. Look away is where Nexi just always looks away. You can kind of see I'm dramatically acting like Nexi won't have a conversation with me. Toy tantrum means that whenever the toy is not right in front of Nexi, it kind of randomly gyrates back and forth like it's having a tantrum. And then my favorite, magnetic control, is where if the marker is behind Nexi, then it acts kind of like an opposite pole magnet, as if it's pushing Nexi to move forward or turn left or right. And one interesting thing here is that through human feedback, I actually end up training control interfaces. So especially with magnetic control and go-to, I'm using this artifact now to control what Nexi does to some level. And so you could potentially use this control interface then to do demonstrations and in kind of this like hierarchical or two-step manner. We never really developed that idea further, but it remains intriguing to me. Here's the training time. On the left, we have the actual time that Nexi's learning. The right includes time of just observing the learned behavior. And go-to is a lot longer because it was the first of the 5, and there was a learning curve as a trainer there. Here are the 5 predictive models of human feedback. You can pause it if you want to take a closer look. Just a review here from the talk. What I covered, other than the intro to Tamer, is a description of how this system for learning from explicit human feedback could be applied to a physically embodied robot, including some of the challenges that were observed and what was done to overcome them. And then the second is explicitly demonstrating the flexibility of teaching by explicit human feedback, which we hadn't done previous to this, but showing that 5 different behaviors could be taught. That ends my talk. Thank you for listening.